even if you don't feel ready, we'll start. Okay, so I'll just point out, just so that everyone has it. There's some hidden stuff there, but the notes after each lecture will be dated, and so you'll have them. Okay, and look at this. We've got assignments locked and loaded for each section. I haven't shown them yet because I want to kind of introduce them first and then give you a week to work on them. And I've posted these kind of shorthand notes that we're going to be working through this week. So not all today, but this week. So usually I do a daily breakdown, but I'm just still trying to figure out the timing. So I figured lump it all into what we're doing this week, up to and including 1.4. Okay, so a little bit of review before we start. We talked about functions, right? And so functions and function notation, generically, f of x is something, some output, where x is the input. And then I said, okay, well, if you want, usually if we have an x and y scenario, like a graph, right, then the output is just y. So if you want to replace the f of x with a y, that works, right? And we worked on some functions, and I left. We didn't have time to finish one of these. So let's see here. The toolkit functions, I've got a document with the graphs for that, so I'll post that. I'm thinking I forgot. This might be a useful thing to look at. These are all little creatures that I expect you to know what they are called and what they look like, okay? And so things like a quadratic means it's something to the power of 2, and that looks like this, right? So usually we're doing pretty good all the way across, maybe up until the cubic. We're gonna maybe need to work on the later half, right? But but love this. But you'll need to kind of get to know these guys, and however you decide to memorize them, it will be beneficial to know these and memorize these. And so you can put them on little sticky notes and put them around your house or your room where you're gonna see them and can talk to them. Hey, cube root. This is actually gonna be what any odd root looks like. Okay? And this is gonna be what any even root looks like. Okay? So once you know the second root and the third root, then you know them all. So that's nice. Okay, so I'll post that because I had forgotten. That's not where I wanted to be. And now it's frozen. Okay. So we said, okay, we talked a lot about functions last day, introduce functions, give an input, find the output, right? Solve for the input that yields some output. Right? Those are all things we're going to come back to throughout the course. And then we said, okay, just because something's not a function, how do we decide if it's a function? The easiest way, right, is the vertical line test, right? So if at any point I cross more than once, then it's not a function. circle. Right? I'm going to cross more than once. And so, but it still exists, is what we said. And so we can still work with these equations. They're just not functions. Okay? And so this is where, let me see if I can copy this into, I wish you could see what I'm fumbling around with here. It's like a big surprise when it shows it to you. I always assume you can see. Okay. So what we said, I guess that's the end of our review, because this is new. We didn't talk about the distance between 2 points, but we can find the distance between any 2 points. Now a point or a coordinate has the form x, y, right? And so if I have 2 points, I'm going to use subscripts, right? So point 1 is going to be at x1, y1, and point 2 is going to be at x2, y2. Okay. Then if I want to find the distance between these 2 points, I can use this formula. And I think that's, no, you don't have to. I'll give it to you if you need it. It's not too bad though. Because what's it doing? It's taking the distance on the x-axis, which would look like this, right? So here's the distance of x2 minus x1. And then squaring it. And then the distance of y2 minus y1, right? A squared plus b squared equals c squared, right? It's just relying on this here, right? Solving for c is the distance between these 2 points, point 1 and point 2. Right? So it's not too crazy, but I don't expect you to get there, right? But well, maybe eventually I will, right? So that here I'll just recall a squared plus b squared equals c squared. So then solving for c, right, where this might be a and this might be b. But like I said, if you need it, I'll give it to you. Huh? But if you break it down, it's not too far-fetched. You can talk about the radius, or the radius squared is a little bit cleaner, right? Just moving that square root over to the r. Now, if we have a circle with a radius r, right? So the distance from the center to the outer edge is the radius at a center of hk, right? So just the x value is h and the y value is k, then the equation of a circle is r squared is x minus h squared plus y minus k squared. Usually circles are centered at the origin, right? 0, 0. Right? And so here I'll do a little special case, because you might be thinking that's not how I remember circles looking, right? And so often circles are centered at the origin, 0, 0. So then r squared is x minus 0 squared. So that's x squared plus y minus 0 squared is y squared. And that might be something you're more familiar with. That's the top. But I feel like that's the building. Yeah. It's just working here. Yeah. Which I'm glad, because it gets really hot with all these windows if it's not going. Okay, so there were a couple of problems that we had left left behind that we can have a look at. Oh, where was I working on this? Here. We have to find the distance between these 2 points. And on a coordinate grid, we can draw this out if we wanted to. What would that look like? I'm just going to do a quick sketch here. You don't have to use the equation if you don't want to, right? But then you need to be able to visualize what's going on. And so let's do this little guy in orange and this little guy in green. And I'll do some fake ticks here. 1, 2, 3, 1, 2, 3. 1, 2, 3, 4. For good measure. I'm just sketching it out. It's not going to be beautiful or anything. Right. X is -3, Y is 4. Okay. So I go -3 for my X. I'll use my pointer. -3 for my X, and then up to 4 for my Y. So that point is roughly there. Not very beautiful, is it? Do the same for the green point. 2, -1, so X is +2 and Y is -1. Puts me somewhere down here. I want to find the distance between these 2 points. Right. So I'm going to draw that here. Let's see if I can pull this off. There. That's the distance that I want to find. Right. Using a squared plus b squared equals c squared, right? You can find that the distance, right? But let's use the formula instead and see. The distance is the square root of, I think we did x2 minus x1 plus y2 minus y1. Oops. This is x1, y1, and this is x2, y2. The 2 x's. That'd be weird. I'm choosing 0.1 and 0.2 arbitrarily. It doesn't matter. Because what happens to the negative when you square it? It's going to make it positive. Right? So don't have to worry about that. So then, using those values, I have x2 is 2 minus x1, which is -3. Square that. Plus y2, which is -1, minus y1, which is 4. Clean this up. 2 minus -3 is the same thing as 2 plus 3, right? 2 plus 3 squared. I'm going to break it down. So 5 squared. You can skip this. You want to jump right to it, but I want to show where everything came from. -1 minus 4 squared is -5 squared. Puts me at the square root of 25 plus 25, square root of 50. Is that 7.1?
Yeah, probably. I don't know.
Probably. The square root of 50. Approximately 7.0710678112. Keeps going though.
Well, for two decimal places, I got correct.
Yeah, so what I would almost prefer is if you just left it in exact form. So the root of 50 is the exact form. So this is what we call the exact form. Now, in engineering though, they love to round, but there's all these kind of sig figs and all those rules that I am not really that up to speed with, because in my field we just use the exact form. But what I would want to see is that you show as many decimal places as you can, and then what you can do is you can say which is roughly 7.07. I'm hesitating because I really want to put the 1. Why do I want to put the 1? Nothing really happens after that 1, so then I feel like I've captured it, right? We put a 0, okay, it would round to 1, blah, blah, blah. But I feel like I've captured a lot of the activity at 3 decimal places in this case, right? If we take the square root, then it's plus or minus. But the distance is always going to be positive, so we've ditched that negative. But technically, yes. So, oh yeah, so you might have, and my calculator does that too. It might show 5 root 2. To get it to the decimal version, you hit the. Yeah, that's fine. I just want to show because maybe not everyone knows how to move between the exact answer and the decimal answer. And so you should have kind of a S arrow, double arrow D on your calculator. On mine, it's above my delete button. So then it'll always give you the exact answer because it's an engineering calculator. But then you can get the decimal answer, which is easier to work with if you're using that number later. So this is the approximate form. So on your calculator, it does all the nice simplification for you. And then you can move between the two. Okay. Good. You can confirm it by finding the distance between these 2 points on the x-axis. Should be 5, right? 3 out, 2 out makes a total of 5. And down 1 and up 4, well, that's a distance of 5. 5 squared and 5 squared, square root, just like that. And I think this is the one that I want to do. Add a page. We're going to find the equation of a circle centered at -3, 5 with a radius of 5. Okay. Now we have the equation of a circle up here. gonna copy it so we can look at it, admire it, use it. First thing we're gonna map out is that, okay, it looks to me like H must be -3 and K must be 5. And also R is 5. X and Y are going to be just variables, so we're just going to leave them as X and Y, because then we'll be able to map out the entire circle. And so here we go. If we have R squared is X minus H squared plus Y minus K squared. What I encourage you to do is just write out, so in your work, write out the kind of empty equation that you're about to use, right? And then it'll be easier to follow your work when you look back on it. Okay. So now I can plug in my values. I have R is 5, so 5 squared is X minus H, which we decided was -3, squared, plus Y minus K, which is 5 squared. Can simplify this. 5 squared is 25. Is X plus 3 squared plus Y minus 5 squared. Resist the temptation, right? Might want to expand this in, but no, no, no. Why? Because what's X plus 3 squared? X plus 3 squared is X plus 3 times X plus 3, which is not just bringing that square in, right? So we have to be a little bit more careful than that. Okay. What do we usually want to do? We want to have it as an equation of Y equals something. Technically, we're done here. If you wanted to leave it here, that's totally fine. But let's solve for Y so that we can have a proper equation. Okay. Or I'm realizing my timing. It's kind of a big one. I don't want to leave it to you guys. How about this? Try it on your own. It's a whopper. Okay. But before I post the notes, I'll add the solution in. Okay. It's kind of too big for us to be working on in like the second week. So it's just for fun, but I'll make a note to myself. Emily, add those solutions later. You can try it, but we got to keep moving. Like I said, this is technically the equation for the circle. I'll put a little good job. You did it. And then it would have to say solve for Y. Any questions before we start the next section, 1.2? So domain and range might sound familiar, right? The domain is the set of possible input values. So the possible values of X. And then the range is the set of possible output values which is going to be your y or f of x. There's some rules that we need to keep track of. We already talked about them last day, just briefly. So we will focus on the domain. We need to be careful of what we put into the function. What we can get out of the function is really just kind of a byproduct of what we've put into the function. And so we're going to focus on the domain of the function. And there are it hurts to say two because there's actually three, but we're not going to introduce it until chapter 4. And so 3 once we are in chapter 4, just so you're not, thrown off by that. But there are 2 rules we need to check for the domain of a function. Rule number 1 is we can't divide by 0. Right? It's impossible to divide by 0. And so, slicing my hand on this thing here. We cannot divide by 0. Okay? It's illegal math. Okay? And so that's the first thing we're going to look out for. So what does that mean? It means that any value of x, so any input value that forces me to divide by 0, I have to pull that out of the domain. And so therefore, any input value, I'll say x, typically. So any input value that yields division by 0 must be removed from the domain. So is not included in the domain. So is not included in the domain. Kind of an example. If I have f of x is 1 divided by x plus 3, for example, right? I have to make sure that I'm not dividing by 0. So then here, this cannot be 0. So then x plus 3, I can treat this as an equation. So x plus 3 is not allowed to be 0, or you can just let it equal to 0 and then pull out any numbers that make that true. You're doing the same thing. So that means that x cannot be -3. Right? Because if x is -3, then I'm divided by 0, which I'm not allowed to do. And so then I pull -3 out of the domain. There are no other values that make me divide by 0. And so that's the only one that I'm going to extract. The second rule is that we can't take the technically even root, but let's focus on the square root. We can't take the square root of a negative number. Okay? Cannot take the square root, but I'll put in brackets even root because it does extend to any even root, but we'll talk about the square root of a negative number. remember from the graph of the square root, right, that it looks like this, which means I can't put in a negative number. I can put in 0, right? Square root of 0 is 0. That's fine. So as opposed to division, okay? But in this case, you're going to pull out any values of x that give me a negative number. Okay? And so we need to remove any values of x that yield a negative number. Usually what we end up doing is, instead of talking about, okay, we need to extract them, so the thing in the square root can't be negative, instead we're going to talk about the ones that we keep. So as an example, if f of x is the root of x, I don't know, I don't want to get too crazy, x plus 5, then I want to make sure that, so I'm going to take an opposite approach here. I'm going to make sure that x plus 5 is greater than or equal to 0. Okay. So then we can force x plus 5 to be greater than or equal to 0, which means that if I treat that inequality as just an equal sign, right, we're going to work more with inequalities, but in this case, it's just an equal sign that we can move around. And so x has to be greater than or equal to -5, which if you check it, right, if x is -5, -5 plus 5 is 0, I'm allowed to do that. But if I let x be less than -5, -6, for example, -6 plus 5 is -1, which I'm not allowed to do. And so here, right, the values in the domain are any values of x that are greater than or equal to -5. Nice. So for now, just those two rules. But again, something I need you to memorize, right, if it's not already ingrained, right, is, okay, we can't divide by 0, and I can't take the even root of a negative number. Often we can find this technical domain, right? So x being greater than or equal to -5, for example, but maybe in kind of practicality, x has to be greater than 0 anyways, right? And so there's going to be a reasonable domain and range. Yeah. And so remember, we haven't talked about the range because I said we'd focus on the domain, because the range is just kind of like following the domain, depends on what you put in. And so, but that's for your outputs. And so we want to talk about what's a reasonable domain and range. So a reasonable domain and range. Right? In theory, if I have a function, usually kind of, what does it look like? Let's think about what this function would look like as we are, I'll move this over so I can draw here. As we start at a low age, well, I'd say we're kind of growing. And then, I don't know, we hit some age where we tend to stop growing. Bless you. I shouldn't go down. but these are all average ages, right? And so when do we stop growing? Let's say 20, just for, that's weird. Probably like, I don't know, what's normal? 18, 17? I shot up and I was like very tall. There, so 20 sold. Yeah, I shot up and I was this height by like, I don't know, very early. And then so I was always kind of the tall person, but I'm not actually that tall. So then everyone just kind of caught up. Everyone thinks I'm tall though, which is pretty funny. So we've got age as the input. That's why I put it on the x-axis, and the average height is the output. Bless you. And so that's going to be on your y-axis. Now, a reasonable domain and range, I would say a reasonable domain is technically this average height would continue to infinity, right? But we stop aging at some point. Let's say, let's max it out at 130, 120, I don't know. We're living for a long time. I don't know, it depends on, it depends on how good it is, right? But in terms of a reasonable domain, we would accept ages up to 130. We would be suspicious, I think. Anything after 130, kind of okay. I don't know how old. We need a Google in here. 122. So 130 is beyond that, but then we've captured the entire reasonable domain. Thank you. Here, I'll put it here, 122. Come on. Why does it do that? Oh boy. I don't know. These things. 122. So it was pretty good about the 130. Right? Can live past that, but not much. And so the reasonable domain, a reasonable domain for age could be between 0 and 130. Now, mathematically, though, this line, if you've drawn a line, it keeps going and going and going. Right? Same thing with the other line. Right? It would just keep going and going and going. So the technical domain would be negative infinity to infinity. Right? But we have this reasonable domain where we would cut it off. So I'm not going to draw that on there. But what's a reasonable range? What's a reasonable range for the average height? Even for the average, a reasonable range could be, I don't know, not really 0, but let's start at 0, right? It could be 0 unitless, 0 centimeters to, now talking about average height, 2 meters on average. That's crazy. Should we bump it up? 2.5 meters? On average. That's crazy. But who knows? knows what can happen, right? But technically, right, because these lines continue and continue to negative infinity, infinity, then technically the range would be from negative infinity, infinity on the y-axis. So just some things to keep in mind. I kept this. Oh, any questions before we talk about intervals? Okay. So we've already kind of introduced an interval here, right? We've got one function on the 0 to 20 interval, and then another function on the 20 to 130 interval, right? And so what we're going to need is just be able to talk about intervals. And I kept this in here because I thought, oh, I can't recreate that. But let's, so intervals. Hey, looks like I had looked it up. 122 at some point last year, I guess. I just forgot. We can change that to 130, I guess. Because that's what I said it was, but that's okay. New example. We'll just pretend it wasn't there. So if x is between 0, as soon as you're born, you are an age, right? And so let's exclude 0 just as an example, and then up to 122 inclusive, right? Because the exclusive, inclusive behave differently in intervals and interval notation. And so I'll erase this because I'll just put it back on there. Oh, they made this update where if you erase something, it switches you back to the previous thing you were doing, and I hate it. Okay, so a couple of ways that we can communicate intervals. So the simplest one being interval notation. Okay. Interval notation takes your start point, comma, your end point. Okay. And so, like we had here, we use round brackets for if we're not, so up to and not including 0. So this would mean it's exclusive, and then square brackets for inclusive. I'll say round bracket is the exclusive. And I'll also add that this is the start point, comma, the end point of the interval. Okay. Probably comfortable with reading interval notation. Right? You can use a number line. Not as clean, but it is helpful if we're trying to kind of visualize things, visualize overlaps, that kind of thing. And so if you're using a number line, we use an open dot for the exclusive and a closed dot for the inclusive. There's a difference there. Okay. Inequalities. You can use inequalities, which are less than, greater than, less than or equal to, greater than or equal to, right? And so the or equal to is this line underneath. So here, this is the exclusive, and this is the inclusive. So x is greater than 0, but less than or equal to 122 is one way that you could read that inequality. Okay. Oh. I'll write this. We'll talk about the set builder notation. Oops. set builder notation is kind of the snazziest way that we can communicate an interval, but we also use set builder notation later on for sets. And so it's worthwhile kind of getting to know set builder notation. And set builder notation looks like this. And so first we start off with these squiggly brackets, which just tell me that, hey, here comes a set. Now we can ignore that, but just know that you wrap it up in curly brackets. Curly brackets for a set. So we have a set of x's, and then we have this vertical bar that says that you read as such that. Okay. So such that, and then we have some criteria. Okay. Notice that we just have the inequality here. And so if you know the inequality version, just stick that in there, right? And then that's the criteria on X. It's a little bit fancier. And what color can I use here, please? Or maybe I'll use the same blue there. The criteria on X. Yeah. Yeah. So as we kind of start with set builder notation, you can kind of ignore a lot of this notation, right? You can ignore the curly brackets, just know that they have to be there. The X is just a placeholder for any element that we're talking about. And then really what we're after here is the criteria, right, on X. And so how we read this, so the set of X is such that X is between 0 is read as the set of X's such that X is greater than 0 and less than or equal to 122. That's how you would read that. Okay. Good. Any questions? All right. The first kind of named set that I want to talk about, and arguably the most important, is most of the time, right? We said that the domain and range is going to be from negative infinity to positive infinity a lot of the time. Okay? And we call that the set of real numbers. Okay? And so the set of real numbers is this kind of fancy R with a double back. You want to draw it all fancy. Okay. And so the set of real numbers is any number between negative infinity and infinity. So then, what does that mean? It means the set of real numbers in interval notation, let's start there, is going to be negative infinity to infinity, We use round brackets because we can never get to infinity. And so we always use round brackets around infinity or negative infinity because we can never get there, right? So it's exclusive, right? But it's more of a concept. Okay? And so we always use round brackets. So that's an interval notation. Yeah. What about set builder notation, which is also going to incorporate inequalities? Well, it's going to be the set of x's such that x is between negative infinity and infinity, right? Which would be your inequality version of it as well. So the set of real numbers is going to be an important player for us. And so it's good to get used to what it is. And it's just any number from negative infinity to infinity. Okay. Let's do some little bit of practice here. We're going to write each of these in interval notation. Remembering we've got the open bracket, so the round bracket, if it's not inclusive, and then closed bracket or a square bracket if it is inclusive. To throw another thing in the mix, for now you can write the word or, but usually we use a capital U, which is the union. So if you want to use notation for the or, you can use a capital U. Give that a go. So the first one's not too bad, right? Just make sure you use your round brackets and your square brackets appropriately and list them from smallest to largest, of course, but that's how they're given anyways. And then the second one is the sneaky one, right? Because first we're told that x is between 2 and 5, inclusive of 2, so I use the square bracket, and exclusive of 5, so I use the round bracket. And then we've got the or, so I'm going to use the union, right? Get used to kind of seeing the union. but you can just read it as or. And then or x is just greater than 8, which means that 8 is actually my lower point, right? Not inclusive of 8, but then to have some sort of upper bound, then the upper bound must be infinity, which again, we use round brackets around infinity. Not too bad once we have the union up our sleeves, right? Then we can link all these intervals together. Okay. What about if we have to write, I'm going to try to use different colors to keep them straight here. But if I have 3 to 6, inclusive of 3, exclusive of 6, set builder notation is really just going to be writing it out as an interval, or as an inequality, and then using that as my criteria. Okay. And so let's say that this is the same as the set of x's such that, and I'll put my x's in the middle because it's going to go between 3 and 6, but it has to be less than or equal to, or sorry, greater than or equal to 3, but less than 6. Close my bracket, right? So the set builder notation is really just asking you to convert it to inequalities, but also write it out as a set. Let's see here. So I've got from negative infinity up to 2, or from 3 up to infinity in set builder notation. I'll start tackling this with the set of x's such that, set builder notation, and then I'm going to use my inequalities. Okay. And so I can start negative infinity is less than x, which is less than 2. And then you can use the union or just the word or x is greater than or equal to 3, but less than infinity. One thing to note is you have to be really careful to not use the word and, right? Because is there an x where it's both of those at the same time? An x that is both between negative infinity and 2 and between 3 and infinity? No, right? So then you've got the empty set, but we don't worry about that. Right? And so then you would have no values in your domain if that's what we're talking about. Okay. So we're going to warm up to set builder notation, but now you've kind of seen it. But it is really just working with the inequalities and stuffing that in as your criteria and just a fancier way of writing it. I misread this briefly. So here we've got a graph of fresh lemons imported to USA from Mexico, but I read it as from USA to Mexico. And that doesn't, why would we do that? Or why would they do that? I don't know. So this makes more sense. Exactly as it says. And then we've got it on the y-axis, we've got the total US highway fatality rate. Well, clearly there's a very strong linear relationship. Now, what's interesting is you can find a lot of these kind of relationships. In fact, I want to show you a website. I think it's called something else, but spurious correlation. So this Tyler Vidgen collects, hey, another fruit one. And he just publishes all these relationships that have a strong correlation, but clearly for no reason at all. He just happened to find these strong correlations. This one is kind of boring. The number of public school students in 9th grade correlates with the Bank of America's stock price. So just keep all your kids in 9th grade, I guess, is my takeaway. Sold. Searches for never gonna give you up correlates with the Google searches for who is Elon Musk. Let's see here. It used to be all these kind of like death related ones, but I guess he's kind of spice things up a little bit, so that's good to see. Oh, the number of movies Will Smith appeared in correlates with the electricity generated. Yeah, electricity generation in Kosovo. Interesting. Anyways, you can check out spurious correlations for just a huge long list of examples. So we're yeah, they are correlated, but can we use that information? Not really. So anyways, just kind of fun. So but we want to talk about the domain and range. Womp womp. I know. Now we've got data points here, and so my domain is going to be quite restricted because I have actual values of x that I'm focusing on, right? And in terms of this line, technically it does expand to negative infinity and infinity, right? Lines just keep going forever. But for us, we're going to focus on kind of the usable domain, or where this line applies, which is only between these points. And so for us, the domain in this case is going to be just the values of x that we're looking at. Now I'm going to bump it out a little bit, because is it reasonable to assume that this line would probably apply a little bit further out in either direction? So I'll go to 200 and 550. Should we get fancy? The domain is all the values of x such that x is between 200 and 550. I went exclusive just because I don't want to be too presumptuous. Right? Kind of an approximate domain. And same thing for the range. We can use interval notation for the range just to flex our muscles here. The range is the values of y. Now I'm just going to look at the values that are given. So 14.8 to 16-ish. 0.8 up to 16 is the range. Remember, the range is for the y, so you don't want to incorporate any x's there. Okay. So, fun stats. What's the saying? There's lies, damn lies, and statistics. Which I'm allowed to say because I'm a statistician. So we already saw a quick example of a piecewise function. So sometimes to model behavior, which is kind of what we're working towards, but also sometimes to kind of capture the relationship of a function, we have to break it up into little pieces, right? So between 0 to 20, we said, then our growth looks like this. And then we said, well, that's not really appropriate after 20. Then I'm going to have this other function, right? And so that's called a piecewise function because we break it up into little pieces. And so the formula that you use depends on the domain and where the input falls in that domain. And so we're going to write f of x is equal to, and instead of just one formula, right, with one domain, then we're going to list the formulas and their corresponding domains with a big curly bracket, just one. For example, if we want to write a piecewise function to describe the cell phone plan, so just right off the bat, regardless of whether you use your phone or not, you're paying $30, right? A base fee of $30. Okay. And then, so that includes 300 free text messages, and then each additional text message costs 10 cents. Those were the days. Oh, I can't. I'm not paying 10 cents? Are you kidding me?
Just receiving a text costs money.
Yeah. Yeah, I know. My mom still says, well, I mean, if I don't read it, then they're not gonna charge me. I'm like, that's not how it works at all, actually. But she's convinced. I can't convince her. Well, I'm just not gonna read it. Anyways, yeah, like if you go to the States or whatever, or maybe you guys have awesome plans, but I'm in airplane mode, living that life. That's good. There's eSIMs too, pretty cool. Anyways, phone plans. Regardless of what you use, right, you're paying $30. So for that first 300 text messages, you're just paying $30, right? And then each additional text message is going to cost 10 cents. So it's going to add 10 cents to that initial $30. Now, one thing that's going to be helpful is first figuring out what the input is and what the output is, right? Get a handle on that. And so let's make a note. The input is going to be called X. And in this case, right, I'm going to put in how many text messages I sent, and the output is going to be the cost for that month. And so number of texts. Yeah, probably, because you don't have to think about it. There you go. So maybe you're paying. No. But then you don't have to think about it. And then this new snazzy phone plan. The output is going to be the cost, right? The total cost, I should say. I'll bump this over. Bink. The total cost. All right. So the output is going to be, I forgot to write it, but I'll call it f of x, right? F of x has two pieces, right? And so I'm gonna draw my, oops, my curly bracket. Take some practice. Okay. $30 is the total cost if x, which is the number of texts, is I'm going to say up to and including 300. Okay. And so here, right, just like we said up here, we're going to say if, and then we're going to give the domain, right? So when do I use this formula? So if x is between, I guess, inclusive 0 to 300. You're allowed to send 0, you're allowed to send 300, but after that, let's assume, it's not clear from the question, but let's assume you're allowed to do 300. And then 301, you start paying. Now, the tricky part is that, okay, so each additional text costs 10 cents, right? And so then what your total cost is going to be $30 plus 10 cents. But you want to be careful because it's not times X, right? Because the first 300 are still free, right? Or free. So if X is less than 300, then you're up here and you're paying 30. But you've already hit, and maybe I should use a different color here. Oops. Minus 300. If I'll use the same notation. What you could do, I'll just show you. What you could say is that if X is greater than 300. But what I would want to do is use the same kind of format where I have a lower end and an upper end. And so I'm going to change this and I'm going to write where if X is between 300, so greater than 300, but less than infinity. You can test this out, all right? If you send 301 text messages, you can do that in your head. How much would that cost? 30 plus 10 cents, right? And so you know what the output should be if X is 301. So then 301 minus 300 is 1. 1 times 0.1, 10 cents, plus 30, there you go. So that's why we have to have the X minus 300 here, because otherwise it's not going to work. Okay, nice. Any questions about that one? Kind of sneaky. The minus 300, I mean. I think if you're following the examples in that PowerPoint that I posted, they have f of 3, which is pretty boring because then none of them are negative. And so I'm changing this last one to a negative, otherwise it makes no sense. we have to evaluate f of 2, let's put it here. If x is 2, then that's going to determine which function to use, right? And so x is greater than 0, greater than or equal to 0. And so then my function is x squared. And in this case, 2 squared is 4. Uh-oh. I'll try writing them like this. Remember, a huge pet peeve of mine is not stacking your equal signs, but I was tempted there for a bit to write it just across. I'll squish them vertically instead. How about f of 4? X is less than 0. No, x is greater than or equal to 0. Again, you can see how boring it would be if we had to do f of 3. 4 squared, 16. How about f of -3? Finally, because I forced it to be, right? -3 is less than 0. So now I'm going to use x minus 4 as my function. Which means I have -3 minus 4. -3 minus 4 is -7. Okay. I'm tempted to graph this or sketch the graph of this. Let's see if I have any space. Okay, I do. We can sketch a graph of this piecewise function. Okay. How? Well, we've got our friends, the toolkit functions. That's nice. So we know the general shape of x minus 4 is a line, right? Y equals x minus 4 has a slope of 1, a y-intercept of -4, right? So I know what that thing looks like. I also know what x squared looks like, parabola. No modifications to the x squared, so it looks exactly like we think it's going to look. And this is just a sketch, remember, so don't, you gotta lower your expectations here. But let's start with this guy. So x minus 4 or y equals x minus 4 is a line. What can you do if you have to sketch it out? Sketching a line, you only need 2 points on a line and then you connect them and you extend the line. So just to sketch it out, what if I let x be 0? Right? If x is 0, y is -4. Let's put that, I don't know, down here, -4. To find the next point on the line, what if I let, I'm picking easy math numbers. What if I let x be 4? 4 minus 4 makes y equals 0. I'm just kind of arbitrarily picking numbers. You could have been methodical, right, and said, what if I let x be 1? 1 minus 4 is -3. That's harder for me to sketch, right? Let's say here, but it would be on that line. What if you let x be 2? 2 minus 4, -2. Seems to be just on that line. So it doesn't matter which points you pick, but this line is going to look something like this. Should probably, how do I wanted to go through both points, but because I didn't sketch this very well, it's not behaving close enough. I can move my dot, I guess. Right. So here I have the general line of y equals x minus 4. Just plop that on there. Okay. Ignoring the domain for a brief moment. X squared, well, if I use maybe orange here, I can start at the origin, and I know when, let's say, x is 2, then I'm at 4. When x is 4, I'm at 16, right? And so here, I get this kind of tight looking parabola compared to my line. Ugh, wonky. Here, this is supposed to be y equals x squared. Supposed to be. But I made my axes so tight, I guess, that it looks weird to fit the 4s on there. So now, what are we gonna do? It's only this line if x is less than 0, which means that, okay, in my function, let's use green. So my piecewise function is going to follow this line all the way down if x is less than 0, not including 0. So how I'm going to denote that is with an open dot at x equals 0. Then it's going to be x squared if x is greater than or equal to 0. So from 0 upwards, it's going to behave like this parabola here. So inclusive at 0, notice how you can't have overlap, right, from the vertical line test, because then it's not a function anymore. And so here it's closed, here it's open. That's allowed, right? Just kind of passes the baton, and then it's going to behave like this guy here. Okay. So knowing the shapes of these functions is going to be really valuable. It just takes practice. Okay. What if we have to write an equation for this piecewise function? Do it in reverse. What can we do? First thing, this looks like x squared, right? We can confirm that it's x squared by saying, okay, if I have 0 squared is 0, fine. 1 squared should be 1, okay, that checks out. -1 squared is 1, good. How about -2 squared is 4? So we've confirmed that this graph is just x squared. Yeah. So what we can do is we can say, okay, f of x is, it looks like there's 2 pieces, right? And so I'm gonna leave room in my big bracket for 2 pieces of this piecewise function. We usually list them starting from the left-hand side, so the smallest value of x, and then moving through to the largest value of x, which means that, okay, from x equals -2, inclusive of -2, up to, but not including 1, it's going to behave as x squared. Okay? And so here we've got x squared if x is greater than or equal to -2 or less than, but not including 1. How about this little guy? We know the domain, right? Starting at 1, including 1, and then it looks like it's going to infinity. You can jot that down. So here, this little guy is going to infinity. So here, if x is greater than or equal to 1, but less than infinity, so we've got the domain portion of it done. What's this equation gonna look like? Well, if x is 1, y is 2. If x is 2, y is 2. If x is 3, y is 2. If x is 4, y is 2. It's almost like it doesn't care what x is. The output is just always going to be 2. And that's exactly what it is. So to make straight lines, right, we just have a constant. And so here, it's just going to be at 2. So y equals 2 looks like that. Right? Doesn't care what x is. You can put in any value of x, and it'll just say 2, 2, 2. Okay. Nice. All right. Do I add? No, let's keep them separate, I guess. Oh, I forget, you can't see. I need you here for my thinking process. So there will be 2 separate notes for today, because I want to keep the sections kind of separate so you can refer to them. Otherwise, you have to scroll through all the days. And so all the days, maybe I should keep 1.1 separate. I'll deal with that later. So we're ready for the next section. Okay. We'll just start it. Okay. That might be good. Rates of change and behavior of graphs. They're American. Has anyone taken calculus? Calculus, yeah, nice. So then you'll know rates of change. Rates of change are very important in calculus, and we're just going to touch in on it. We're not going to do any calculus, but kind of building up to the concepts. And so a rate of change describes how the output quantity, so the y, changes in relation to the input quantity, so changes in relation to the x. So how fast are you increasing or decreasing? And visually, what does that look like? If you compare these 2 graphs, just briefly, right? If you've got a line that looks like this versus a line that looks like this, assuming you're on the same scale, right? This is a slow rate of change. You can see that, right? And this is a fast rate of change or a large rate of change, right? And so it's really just going to be talking about the slope. But units get a little bit trickier just because the rate of change is the rise over run, right? So the output units per the input units, right? So rise over run is the slope, just like we were seeing here, right? We're going to be talking about the slope essentially. And so don't get me started on rats. I can talk for a disturbingly long time about rats because I really don't like rats. And for some reason, it's an obsession. This year, for the first time, they're having the Urban Rat Summit in New York, where they're trying to come up with ways to combat the population of rats. There's a couple of interesting options floating around there. But anyways, like I said, I can talk for way too long about rats, which I don't even like. Imagine how long I can talk about dogs, which I do like. A population of rats increases by 40 rats per week. Okay, fine, one more. So they did a study in New York, and very interestingly, I think it was a 7-block radius, if you move 7 blocks away, the DNA of those rats are completely distinguishable, which is crazy, right? You think they're running around town? Nope, they're just living in their little tiny block, and that's just where they are and where they breed, and they don't really stray. It's crazy. Anyways, rats, don't get me started. A barista, I can't talk about. I can't talk about baristas for that long. A barista earns $9 per hour. Oof, dollars per hour, and then a farmer plants 60,000 onions per acres, right? So we've got our input and our output. Okay, so per week, so the week is the input, per hour is the input, per acre is the input, right? Okay, so the average rate of change between two input values, right, is the total change. So the average rate of change, you're going to be talking about the change of the output over the change of the input, which we can denote by delta. Delta is change. Yeah, and it's true. But does anyone ever call it delta? No. There you go. Yeah. Well, now you know it's actually the Greek letter delta. Is it the capital or the lowercase? I think it's the capital delta.
Yeah, I think so too.
Because I feel like the lowercase delta looks like this.
Yep.
Right? Something like that. I think it's the capital, but yeah, sold. So delta, we use delta for change. Apparently shorthand everywhere. Cool. And so delta, which means change. So the change in y over the change in x, this is starting to sound a lot like rise over run. Right? And it is, right? Your change in y over your change in x, right? If you just want to morph that into rise over run, you might have something like this, right? So let's do we'll draw a line here. Just gonna pick 2 points arbitrarily on here, right? And what can I do here? I can denote this as 0.1, x1, y1, which we've actually seen already today. Uh-oh. So something to be comfortable with, x2, y2, just generically speaking, any point 1 and 2. And then, let's see here. What color can I use? If you go back to your rise over run, the rise is going to be what? The rise is going to be the distance between y2, whatever it is, and y1. If you did y1 minus y2, then you'd get a negative number. That's okay, because your x's would be 2, but just to eliminate that, we're going to use y2 minus y1. It saves us some work. I hate negatives, so I avoid them at all costs. Yeah. By taking y2 minus y1 instead of y1 minus y2. But the distance is the same, right? And so that's what's important. So then, if I talk about the run, must be from x1 to x2. But if I did x1 minus x2, then I would again get a negative number. So if I did them as 0.1 minus 0.2, I'd get a negative over a negative, which would cancel out and it would become positive. So it doesn't actually matter, but just to not have to work with that, the run is going to be x2 minus y. Oops, nope, x1. So then the average rate of change is y2 minus y1 over x2 minus x1. I shouldn't have done that yet. I'll put it here. Put her there. Is the rise over run. Skipped straight to the equation. But it is rise over run, and if you take the rise over the run, then you get y2 minus y1 over x2 minus x1. Okay, we'll just do this example, and then I'll leave the rest for Thursday. Given the function below, the function's given as a table, which we saw last week. Okay, we're allowed to do that, we can do that. And we know how to read it. I give it an output and it returns some, I give it an input and it returns some output. Yes, technically the reverse is true. We want to estimate the average rate of change on each interval. And so let's do A on 4 to 8. Okay. X1 is 4. And the output of 4 is 6. Giving me y1 is 6. Input x is 8 gives me an output of 16. So then the average rate of change is going to be y2 minus y1 over x2 minus x1. And try to keep it on this one page. 16 minus 6 is the change in y, or the output, and then the change in x is 8 minus 4. 10 over 4. Trying to find a way to keep it on the same page here, but can I do something weird like this? Because I've got a page break here. Right? Whew. So here, the average, it's the rate of change, but you can see I'm kind of struggling for space here. So the first input is 4, okay? And the second input is 10. So now I have an output of 26 instead. So I have y2 minus y1 over x2 minus x1, which is going to be 26 minus 6 divided by x2, which is 10 minus 4. I'm getting 20 divided by 6, which I don't think. 20 divided by 6 is roughly 3.33 repeating, and 10 divided by 4 is roughly 2.5, or it is 2.5, but habits. So then we have a faster average rate of change between 4 and 10 than we did between 4 and 8. Step away from the plate. I'll leave it there, but you can try this next example on your own, and we'll pick up there as review on Thursday. If you have any questions, let me know. Oh, one last note here. If you are printing these notes, you need to add about 4 pages for showing work, roughly. Obviously, I print really large on these once you print it to PDF, so my pages, but just as a heads up, you'll need to be able to kind of insert work there that I didn't make in the PDF. Because that's annoying when you find out that you printed just blank pages, especially if you're paying for printing. All right, stop this recording.